I'm going to have to ring that bell louder and earlier, aren't I? Come around and chase you. Okay, so hopefully you're enjoying the conference so far. On to our next speaker. So our next speaker is going to talk a bit about immutable code analysis using tools analyzer. So I'll hand over to Nikolai. I just want to mention that Nikolai's actually a Clojure contributor as well, so it's great to have him here to talk about this. I'm going to thank him. Thank you. Thank you. And thank you, Robert, for reminding me. So over to Nikolai.
All right. So those are my contacts, if you want to contact me. So today we're going to talk about Tools Analyzer, which is a library that deals with doing analysis over Clojure code. But before diving into that, I want to guide you into the Clojure compilation pipeline using CNC. CNC is an umbrella term that I use to describe the set of contrib libraries that I wrote, of which Tools Analyzer is part of, that together play to make a Clojure compiler. So the life of a Clojure expression starts with the reading phase. And reading is handled by Tools Reader in the CNC architecture. What reading does is it gets a string of characters representing the program that we're going to use, and it transforms it into a data structure. The Tools Reader library is composed of 3 different modules. One is the Clojure reader, one is the hidden-only reader, and then we have a bunch of text readers that are similar in the functionality that they provide to the Java I/O readers. So we have, for example, the string reader, the indexing reader, which just annotates whatever it's returning with line and column and file name information. And then we have the source logging reader, which is the most recent addition, and it's probably the most interesting reader of them all. And it serves to return to the Clojure reader the context information of the token that is currently reading. So this is used, for example, by Clojure script to provide accurate source mappings that are white space and comment aware. And this is how you get your nice stack traces in Clojure script and all that code. So once Tools Readers has read the code, all it does is take this data structure representing the code and pass it into the next actor in the pipeline, which is the analyzer. The analyzer is, in this case, Tools Analyzer, or more specifically, Tools Analyzer JVM. And I'm going to explain later what's the difference between those 2 libraries. So what the analyzer does is takes this form from the reader. It does some steps over it. So the first thing that it does is it macro expands the whole form until all that's left is just primitive operators. So something like numbers, strings, or symbols. And function call or special form invocations. So either a function call or an invocation to something like do or let star or other special forms. After it does that, it also takes care of inlining all the functions that Clojure Core provides an inline implementation for. So stuff like inc is inlined to the actual Java static method. After it's done that, it parses all this expanded code into an AST. And once it has this AST that is just going to be Clojure maps, it does some additional analysis over it, and it passes it to the emitter. The emitter is the last actor in this pipeline, and it takes the AST from the analyzer. It can optionally transform it can optionally transform the AST into an internal representation, and then all it does is just takes this internal representation of the AST directly and emits the actual code, or bytecode in the case of closure on the JVM. Finally, it can even load the code in memory. That's what, for example, eval does, while compile just sidestep this last operation and just emits the bytecode. Just a moment for this phase in the actual emitter for tools analyzer. So what tools emitter does is, I think, quite interesting, because it takes this whole codes data to the next level by representing not only classes and methods, but also the actual bytecode as a data structure. So what this enables us is to use the same functions that we're used to manipulating data to manipulate the actual bytecode. So what I'm planning on doing in the future is to use something like core logic or core match to pattern match over the bytecode that's going to be emitted and figure out what kind of people optimization we can apply to it. All right, with this architectural overview in mind, we can finally look at what Tools Analyzer does and how you can use it. So when I first started developing Tools Analyzer, I had three big goals in mind. I wanted it to be dialect agnostic, and by that I mean that I wanted the same libraries to work on both Clojure and ClojureScript. I wanted it to be platform agnostic as well. So I wanted code that was written for Clojure on the JVM and code that was written for Clojure on the CLR, for example, to be analyzed by the same analyzer. And to do that, I wanted, obviously, to have the AST common between all those different combination of platforms and dialects. I also wanted the analyzer to be data-oriented. And this is something that I decided I wanted after seeing the ClojureScript analyzer and how it deals with ASTs as data. And I don't think I have to mention why data is good for us, because we are Clojure developer and we know why it's important. Finally, and probably the biggest goal that I had in mind, is I wanted the analyzer and the compiler to be multipass and really multipass. I didn't want it to be just one or two passes over the AST like the original compiler is. So why is that? Because I intended the analyzer to be used not only for backend the compiler implementation, but I wanted it to be useful for tools authors and for whatever reason you could want to want analysis over some Clojure code. So having it multipass would enable us to selectively choose which passes to apply to an AST and to selectively disable a bunch of passes that we don't need to. Moreover, I wanted users to be able to come ask me, for example, how is this pass implemented in Tools Analyzer? And I didn't want to have to do what I have to do on the Clojure compiler and to say, okay, so this is the block of code that deals with local squaring, and here after another 300 lines of code mixed in between the logic that does line numbering and all that kind of stuff is another bit of logic that does that. What the heavily multipass design allow me to do is to give them, okay, this is the file that just does this and nothing else. And all the logic that deals with whatever you're asking me is here. So let's see how Tools Analyzer actually overcome those original goals. The first thing that I did was to split the libraries into multiple libraries. So we have Tools Analyzer, which is a general library that does only the analysis that's common between all the Clojure dialects. Then we have a bunch of Tools Analyzer .something libraries. So currently the only implementation are Tools Analyzer.jvm and Tools Analyzer.js that deal with Clojure on the JVM and ClojureScript respectively. What is in Tools Analyzer is a bunch of analysis that returns generic AST nodes. So, for example, if you think about the dot form for interop, it's something that's common for both Clojure and ClojureScript, but in the different dialects, it means different things. In Clojure, it might mean static method invocation or instance method invocation, while in closure script, it just means get a property from this JS object. So what ToolsAnalyzer does, it just returns a generic node that says, okay, this is a .form, and ToolsAnalyzer.jvm is responsible for telling him what it actually means later on. Then we have to figure out what the entry points that every dialect requires. And those are the macroexpander, the parse function that deals with telling ToolsAnalyzer what additional special forms each dialect has, and what it means to be a var in this dialect, because Clojure has reified and real vars, where ClojureScript just has compile time vars. Finally, the namespace system was completely abstracted away. So in Clojure we have a mutable namespace system, while in ClojureScript we have an atom holding an immutable map. And this is what ToolsAnalyzer does in this .env namespace. It abstracts both the namespace system into a common namespace system. All the stuff is implemented either with dynamic vars that can be rebound by the correct implementation, or by multi-methods that gives us open dispatch. Data orientation. So I went with the ClojureScript way of representing AST nodes as maps. The node type is under the op key. Every AST node has a form key that holds the original form that this AST node represents. And we have an env key which holds not only the lexical state of the analyzer at the point of analysis, but the whole state of the analyzer. So we can find stuff like what locals were available at the point of analysis, whether this expression is part of a loop and which loop this expression is part of, and all that lexical stuff. All right, but we know that data is cool and we want to represent our stuff as data, but it's also important that we are choosing the right representation of our data so that it can allow us to do whatever we want with it. So this is an example of what an AST node might look like, and indeed it was what I originally chose as representation for AST nodes. We see that it's a node with op type foo and two children nodes, one of which is just a single node of type bar, and the other is a collection of nodes, one of which is of type bar and other are potentially other nodes. And we have some meta information about the node. What does this representation give us? It's easy to update it because we can use update in or update. It's easy to look up because everything is indexed by keys, so we can use get in, and whatever we want. What it doesn't give us is the ability to traverse nested nodes in a generic way, because we don't have any way to say, okay, child 1 is a node, child 2 is a collection of nodes, and some info isn't. We don't have any explicit representation of what nodes are in this, what child nodes are in this AST node. And it also doesn't encode any information about what the ordering of those two child nodes should be. So we don't know whether, suppose this was an if statement, and this might be the test expression and this the then expression. We don't have any way of telling whether this test expression should be evaluated before the then expression. All right, so another potential representation would be to encode the children nodes inside a children map. This gives us easy update, lookup, and traversal because we know what the children are, but this still doesn't give us the property of knowing what the traversal order of the child nodes would be. So how can we solve this? All right, so we know that vectors are an ordered collection, so we just stick the nodes inside a vector. All right, we get now the explicit traversal ordering and the easy traversal, like the previous representation, but we lose the ability to be able to easily look up and update the nodes because we've moved from a key value representation to an index representation. This is how ClojureScript solves this problem, by duplicating the information both in the children vector and in the original AST node. And it's quite there, but not fully there yet, because we trade ability to have easy lookup and explicit traversal ordering, but we lose the ability to have easy update, because now we have the same information duplicated in two places, and whenever we want to update this children node, we have to be careful of updating the equivalent children node inside the children vector as well. So what tools analyzer does is it represents the children nodes. The children node in the top level AST nodes, and it keeps a vector representation of all the keys that maps to those children nodes. This gives us easy updates because it's just keys on a map and easy update. Traversal is easy now because all we have to do to be able to understand what nodes are actual children node is to just look at the children vector and figure out the keys that this AST node maps to. And the ordering is explicit as well because this is an ordered collection. All right, so having the correct representation is not enough, unfortunately, because we need the ability to generically traverse it. So in Clojure, we have already a core library that deals with traversing nested collection, and that is Clojure Walk. So my first attempt was to use Clojure Walk directly. It turns out that it's not a good fit because it's too generic. When we want to traverse this AST, all we want is to traverse the AST nodes. We don't want to traverse the meta information about it. We don't want to traverse the env information. So what I did was to provide a walk-like API that is AST aware. So we have, for example, AST children, which just returns an ordered vector of all the subchildren of the current node. We have pre-walk and post-walk functions that just run a function over the nodes in the AST in the order specified. We can give an optional reverse option to post-walk. So that means that the post-walk will be in reverse evaluation order. And this is useful for some complex analysis like local clearing that needs to look at the last node that is invoked. And we have another bunch of functions that are really useful. So we have walk, which is the generic function on top of which pre-walk and post-walk are implemented. Update children, which is just which is like walk but is just one level. And node which takes an AST and returns a collection of all the nodes flattened out. Think of TreeSeq, for example. And the cool thing is that all these functions are implemented in terms of reduce. What it means is that we can use reduce to early terminate every walk that we're doing for free. All right, so on to the final goal that I had in mind, the multipass architecture. So if you look at the tools analyzer code and the tools analyzer.clj implementation, it does very little. It's just 1,000 lines of code to do analysis on all Clojure and all the Clojure forms. Why is that? Because all the actual analysis is done by some small composable phases that are run on top of that AST, using those same functions that I just showed you. Every phase is optional and configurable. So that gives every user of the library an incredible power over what the analyzer will actually return. Those phases are combined into different logical actual passes over the AST. So, for example, in Tools Analyzer provides about 30 phases that are combined into just 5 actual passes over the AST, and that gives us incredible performance enhancements. What are actually those phases? They are just multi-methods. They're just functions that dispatch on the op key of each AST node. They take this AST node and they return an updated, a potentially updated view of that same AST node with all the additional information that they require to insert. All right, but okay, we have those phases and they're just functions, but how do we combine them? How do we run them over the AST? So in the initial, for the initial 1.5 year, I had to manually combine them using cons and using comp and ordering them manually, so that if a phase required some information that was installed into the AST by some previous phase, they would be in the right order. That turned out to be a really expensive operation for me, and it turned out to be really error-prone, because every time I need to change something in some phase, suddenly everything stopped working. So what I did was to write a scheduler. So all the phases that are provided by Tools Analyzer now declare what the work order that they require is, what their dependencies are, and what are the phases that they affect. The scheduler just deals with resolving transitive dependencies of those phases and combining them in the optimal order. All right, so that's it for the overview of how the architecture works. How do we actually use it? So the public API of toolsanalyzer.jvm provides 4 basic functions. We have 2 functions that deal with analyzing an actual closure form. And a common mistake that people do when trying out Tools Analyzer is that they use analyze. You should never use analyze until you really know what you're doing, unless you really know what you're doing. Why is that? Because the evaluation model of closure requires every form to be evaluated before the next form is evaluated. If we don't do that, macro expansion will probably break in some cases. It might work, but only if you're lucky. So if you're looking for analyzing a program form by form, use analyze plus eval. Otherwise, we provide an analyze/ns function that just takes a namespace name and returns a vector of all the ASTs corresponding to the top-level forms of that namespace. Finally, Tools Analyzer.jvm provides a macrospend all implementation, which is similar to the one that Clojure Work provides, but is lexical environment aware. So if a local shadows a macro, we know that, while Clojure Work doesn't. And then we have a bunch of vars that just deal with providing same default for all the phases and all the passes provided by default. Here is a link for the reference to all the node types that Tools Analyzer.jvm returns. All right, but let's see how it's actually used in the real world. So CoreRacing uses Tools Analyzer.jvm as its analysis engine, on top of which the Go macro is used. CoreType uses Tools Analyzer.jvm as well to build the AST on top of which the actual type inference work is done. Eastwood, the popular linter that I hope all of you use, if not you should, uses Tools Analyzer for some of its most complex linters, where just looking at the closure form is not enough. And finally, CLJ Refactor, the tooling that we heard yesterday talking about, uses Tools Analyzer for some of the refactoring tools that would be impossible without an actual AST. And finally, something that not many are aware of, Tools Analyzer provides an data log aware transformation for Tools Analyzer ASTs. So you can query every Tools Analyzer AST with Datomics datalog or Datascripts datalog, and it just works. What's gonna happen in the future? A bunch of things. So probably the most important thing is to bring Tools Analyzer.js up to date with the most recent ClojureScript work. Rewriting the method matcher, because the current implementation in the Clojure compiler is just nuts, and I try to rewrite it to be same, but it turns out that it's impossible to keep the correct semantics without using what Clojure actually does. And then a bunch of things with tools emitter, faster implementation and AOT support. And something that's really bugs me is that I'm the sole author of all those libraries, and I would love some contributors. I have a bunch of people to thank for this work. So most of the initial development has happened thanks to Google Summer of Code. Ambrose Bonner-Sergeant is the developer for CoreTyped, and he's run a bunch of successful crowdfunding campaign, and he's decided in 2013 to give some of the money he raised to sponsor the tools analyzer development. Cognitect has been sponsoring tools analyzer development for a year, and I want to thank Timothy Baldridge, the author of the Go macro, and Alex Miller, because I regularly bug him about what I think is broken in Clojure, and he's just great. And finally, I want to thank Andy Fingerhut, who was in 2014 has opened like 50 tickets on the Tools Analyzer issue tracker, and Tools Analyzer wouldn't be as stable as it is without all the testing that Andy has done. He's the author, he's the maintainer of the Eastwood linter, by the way. So that's all I had. If anybody has questions,
Hi. I was wondering to use it for source code tools, how does it deal with incomplete or invalid source code, and also whether it retains white space and comments?
So Tools Analyzer is designed to work with correctly formed Clojure forms. So it can't really deal with stuff that's not going to evaluate in Clojure. It's a Clojure analyzer. It's not something that was designed to work with partially working forms. So the short answer is that it doesn't, but it actually somehow can do it, because we provide hooks into the analyze phases that do validation. So if you're smart enough and you understand what the analyzer should do if it encounters a form that's not really correct, then it can work around it, because it's open and you can just change the default behavior. It's going to be tough, but you can do it, and the CLJ refactoring guys actually do something like that. And for the white space aware thing, it's not, because after we read, we lose all the white space awareness.
This whole multi-pass compiler thing is really interesting. I'd like to know how you learnt about it and where I can go and learn about it.
So there was an interesting paper there was actually a talk about it during Clojure Conch 2013, I think, and it was called I can't remember, to be honest. But it dealt with what they called micro passes, and it was a paper in Scheme where they implement a compiler as a collection of micro passes over DST, and it's much more multipass than the Tools Analyzer implementation, because we have only 30, but we use 20 passes, and they use like 80 passes over DST. So I'll link the paper in the slides, and you can have a look at this. Yeah. Okay, so my time is up. So thank you.